Hi everybody, my name is Elena McHale and I chose the software vulnerability race conditions to present on today. Um, in order to really explore this topic, I'm going to be getting into a general description of this vulnerability, how you can identify a race condition, an introduction of some basic examples of race conditions, how you can mitigate this vulnerability, and finally give you a real life example with a CVE. So let's get into what a race condition actually is. So a race condition occurs when there are uh, two or more threads sharing and accessing the same data. So the program will be highly dependent on the timing of each process to function properly in this case. The thread will run or finish at the same time that's unexpected and give an incorrect output or cause a program deadlock as a result. So this happens because you don't know for certain the order which the threads are attempting to access / change this information. It's called a race condition because multiple threads are essentially racing to change or access the data at the same time. So one thing to note is that a race condition is a semantic error, which means the flaw occurs in the timing and the ordering of events. So when identifying a race condition, it is kind of tricky to approach it as just a semantic error, simply because when you talk about a semantic error, there's not really a way to detect them because there's not an automated oracle that can distinguish a correct behavior versus an incorrect one that the user intended a program to execute. But there is a way to detect data races. So there are data race detectors that include things like static and dynamic data race detection, lockset based detection, happens before base data race detection, and then a hybrid of those options. So I think race conditions will be better understood if we get into a couple of examples. So let's look at this first one. So problems that typically cause race conditions usually occur when the thread does a check and then an act, and another thread does something to the value between that check and act. So it sounds like a little confusing just saying it out loud, but I think this example is going to make that more clear. So here we have the check as x being equal to 10. Then our act will occur when that 10 is multiplied by 2. So in between that check and act is where our error would occur. So for example, a race condition could occur in this example in particular if a thread changes x between the if x is equal to 10 and y equals to x times 2. So let's say the second thread changes x to 5. So we would expect the output to be 20 if the race condition didn't occur. But since it did, we wouldn't have y giving us an expected 20. Okay, so let's look at another example that is similar in the fact that it has the same check and act, but it behaves a little differently here. So in this one, we have our check here, and then our act. So it's executed, and of course, this is where our race condition would occur. So in this example, let's say that the thread receives the value for x, but doesn't have the opportunity to store that value before another thread comes along and tries to change x. So another thread could receive the same value of x because it wasn't stored, and then they would both be storing the same value, which would result in unexpected results. So let's say that thread 1 reads X, and let's just say X in this example is the number 7. So thread 1 would execute its act, which is the X equals X plus 1, which will now make 7 into 8 being stored for X. But then thread 2 can come along and read the value as still being 7, just because thread 1 hasn't had the opportunity to store the result of its act, which was 8. So then thread 1 is now storing 8 at the same time as thread 2 is adding 1 to 7 again, giving the same result of 8 for the value of X. So now we see the problem of both threads now storing the same value for 8, which will cause the result to come out incorrectly, or I guess I shouldn't say incorrectly, but just not correct for the user's expectation. And we would expect a result of 50 million here, let's say, but we would not get that if the race condition occurred. So typically someone could avoid a race condition just by placing a lock around that shared data so that only one thread could access that data at the same time. But you could also use condition variables or semaphores. On this slide, I just have the locks. On the previous example, it doesn't show that condition variable or semaphore. But you could also use paradigms like message passing instead of shared memory to avoid data races entirely. So now let's talk about a real-life occurrence of a race condition, since we understand a bit more about the general idea of a race condition. So CVE 2020-8833 suffers from a race condition error. So essentially, in this CVE, a time of use race condition vulnerability occurs on the ownership change of the crash report. So this can lead to a possible privilege switch. So if fs.protected semlinks is disabled, then there can be exploits between the os.open and the os.shown calls when the apport cron script clears out any empty crash files. So a symlink with the same name as a deleted file can then be created changing the file owner, which is actually where that race condition occurs. So some fixes for the CVE include using reportFile.fileNo function instead of using just simply a report string for the os.shown calls. You could also remove the size 0 conditions in the cron script. Then, if you just want to be safe, you could also add a follow_symlinks equals false argument, and this would just assure that it's not being even read in. So I hope this presentation gave you a better understanding of race conditions. If you're still curious, there's several other CVEs that also suffer from race conditions, so I would definitely encourage you to check those out. And there is also a lot of popular examples in real life businesses that we're all familiar with that also have had issues with race conditions, if you just want to explore a little deeper into what this vulnerability actually is.